Today, we have the honor of having Amy Bauer present in this AMOC webinar series. Amy is a senior scientist at Woods Hole Oceanographic Institution and the chair of their Physical Oceanography Department. She is part of the U.S. AMOC Science Team and contributed to the AMOC State Variability and Change Task Team, also known as Task Team 2. She has been the PI on several AMOC research projects, including one to make a modern estimate of the mean transport of Iceland-Scotland overflow water, one of the deep components of the AMOC through the Charlie Gibbs fracture zone, and understand the processes that cause strong variability in that flow. She is also a co-PI on OSNAP, in which she is responsible for the study of the pathways of the deep limb of the AMOC in the subpolar North Atlantic using Rainfall's floats, and maintenance of the DWBC mortar ray in the Erminger Sea. In today's presentation, Amy will provide a summary of the paper in which she led as part of the AGU Special Collection, Lagrangian Views of the Pathways of the Atlantic Meridional Overturning Circulation. Please go ahead, Amy.
Well, thank you very much, Jenny, for that introduction and for the invitation to present a very quick tour through this paper that was published last year on the Lagrangian views of the AMOC. This was a highly collaborative effort, and I've listed the co-authors there on the first slide and their affiliations, and I'm grateful to all of their contributions. There would have been no review paper without them. We go to the next slide, slide 2. Most of us are very familiar with this iconic figure schematic of the Great Ocean Conveyor. It elegantly and simply captures what we now know about the connectivity of ocean circulation across all the major ocean basins. But if it's taken too literally, it perpetuates a perception that the global MOC, and the AMOC included, is a simply connected system of currents where changes in one part of the system will be communicated immediately everywhere else, just like a conveyor belt. It's one continuous loop. But Lagrangian observations actually show something quite different. And we believe that it is important to include this Lagrangian perspective in our studies of the global and Atlantic MOC to make sure we fully understand the complexity of the system of currents that makes up the MOC. Where Lagrangian observations are sparse, which is through a large fraction of the ocean volume, we also can use numerical fluid particle simulations. We can use them in great numbers and do some interesting things with them that we can't do with observations. And so they add another Lagrangian tool to help us understand the complexity of the MOC. They are, of course, much cheaper. You can, quote unquote, deploy thousands of them at a time. And you can actually track particles forward and backwards, which we can't do with observations. We could go to slide 3, please. In our paper, we use multiple Lagrangian tools, including surface drifters, and subsurface acoustically tracked floats, profiling floats such as Argo floats, and simulations from numerical models of fluid particle trajectories. In this slide, I just sort of summarize a little bit about the acoustically tracked floats. The 3 panels show the data coverage for the whole globe at 3 different depths of acoustically tracked floats. And then there's a small animated video there that sort of shows how these work. For those of you who don't have any experience with acoustically tracked floats, they are deployed from a ship, usually. They sink down to a predetermined depth. They have a hydrophone on them, and they listen for specific signals from moored sound sources that have been deployed before you started the float deployments. And they listen for these signals. They record the times of arrival of those signals, and then we convert those times of arrivals to ranges or distances from each sound source and use a triangulation process to determine the float position. This is all done after the fact, after the float has been drifting for, say, up to 2 years, collecting all this sound signal information. It returns to the surface and transmits the data through satellite. But we recently put together a database of all such acoustically tracked floats going back to the 1970s, and the predecessor of what is now used, which is the Rafos float, which is what I just described, and what is pictured here, the SOFAR float was the first such subsurface acoustically tracked float going back to the 70s. Okay, if we could go to the next slide, please. AMOC upper limb, South Atlantic. So the way I'm going to proceed here is to march through sort of the conveyor belt path, starting with the upper limb of the AMOC in the South Atlantic. This section of the paper reviews the relative importance of the cold water and warm water pathways of the South Atlantic AMOC. The warm and salty pathway originates from the Agulhas, and the colder and fresher pathway originates from Drake Passage. And both of them are, relatively light upper ocean waters, so they can both participate in the upper limb circulation of the AMOC. But of course, they have very, very different thermohaline properties and different pathways. The figure here shows a subset of simulated trajectories, because to get at the sources, like which of these two sources contributes most significantly to the AMOC, we really don't have a surface drifter data set that can address that with any statistical confidence. So in this case, we relied mainly on studies of from simulated trajectories using an eddy resolving numerical model. And there's some examples of, this is also an example of backtracking, where you pick a point, in this case, the North Brazil Current, which is a known choke point for the northward AMOC flux transport. And you can go backwards in time using the model to figure out, okay, particles going through that choke point, where did they come from? And if you use thousands of trajectories, numerical ones, then you can start to get some statistics on which source is dominant. So just to, this sources and their relative importance had been, and probably still is to some extent, controversial. But in this particular study and another observational study, it was found that about 60% of the source is from the Agulhas leakage, and about 40% from the cold water path around direct cold water path from Drake Passage. On the right, you also see the transit time distributions, which you can calculate from these simulated trajectories, and they show that the path from the Agulhas is a bit quicker than the one from Drake Passage, which that path goes all the way around the subtropical South Atlantic gyre before reaching the North Brazil Current. So it has a bit of a longer trek. Okay, so if we could go to the next slide, please. We're going to move now to the upper limb tropics of the Atlantic. Here we're going to turn now to some observations from surface drifters. In this figure, you see a subset of about 5,000 tropical surface drifters, and that were selected based on whether they pass through one of two boxes. There's two different panels. One box is, again, the North Brazil Current box, that's on the right, and then on the left is a Yucatan Channel box. So the point here is, again, those are two choke points for the AMOC. where do particles come from that pass through those choke points, and then where do they go? That's the question we're after with an analysis like this. So there's really, as I said, this is going to be a really fast tour. If you want details, I suggest that you read the paper. But the main point I wanted to make here is the contributions to the North Brazil current box comes from the South Equatorial Current and shows this zonal path across the Atlantic, or part of the Atlantic anyway, to join up with the North Brazil Current. So we often, we will always refer to the AMOC, Meridional Overturning Circulation. But my main point here is that the three-dimensional structure of the AMOC has zonal components to it, as well as meridional components. And this is one of them. This is an example of one of them. Okay, I could go to slide 6, please. I'm going to jump northward now. We're still in the upper limb to briefly discuss some interesting results that have come from observations and numerical simulations. Back maybe a decade or so ago, scientists were looking at surface drifters deployed in the subtropical North Atlantic, primarily in the Gulf Stream, which is thought to be the primary conduit for warm water going northward in the AMOC up to the subpolar latitudes. Gulf Stream to the North Atlantic Current or the North Atlantic Drift, and then into the subpolar region. But if you look at all the thousands of surface drifters that have been launched in the Gulf Stream over the decades, very, very few were shown to go to those northern latitudes in the subpolar gyre. And that presented quite a conundrum, because it seemed to indicate there was almost no connectivity between the Gulf Stream and the subpolar gyre. And that we're scratching our heads about that. But this figure shows a resolution to that conundrum. It shows the trajectories of some profiling floats. This is sort of pre-Argo days, but profiling floats that were launched in the Gulf Stream at depths between, I think, 300 and 1,200 meters. Most of them are at 900 meters. There are about 9 tracks here. And these profiling floats drift for maybe 10 days or so at depth, and then they pop to the surface briefly to get their position, then they go back down. So you see little gaps between the trajectory segments. But what this figure shows actually is some low number of observations, but considerable connectivity between the Gulf Stream and the eastern subpolar region. And this showed, along with subsequent numerical simulations, that it isn't the surface waters of the Gulf Stream that stream directly into the eastern subpolar gyre, make on their way northward. It's subsurface waters. And that's what these floats are tagging, are subsurface waters. And they they do show evidence of a direct connection between the Gulf Stream through the North Atlantic Current and into the eastern subpolar gyre. And as I said, numerical simulations of surface drifters, so two-dimensional velocity fields or particles released or initialized in a model, show again this lack of connectivity. But if you go below the surface to the upper thermocline, for example, there's actually significant connectivity there. Okay, I'm going to, in the interest of time, I'm going to skip the next slide, slide 7. That makes more of the same point, really. So now, slide 8. Now we're marching along, continuing northward now from the subpolar into the Nordic seas. And I'm not going to get into the details of this because you could spend a long time on this. But the main point really here is to illustrate an advantage of a Lagrangian, the Lagrangian approach, whether it's observations or simulations. In this case, it shows a gridded velocity field that has been obtained from thousands of surface drifters in the region of the subpolar to Nordic seas connection over the ridge. And the advantage of floats and drifters is that they spread out all over the place. And so you can take their velocity measurements, which they make naturally from the distance they travel divided by the time, so you get velocity estimates along the tracks. You can bin those velocity estimates geographically into small bins, say 1 degree by 1 degree or whatever. And then you can come up with a map like this of velocity. And you can actually then see patterns of the velocity. And, this is a really valuable aspect of the Lagrangian method, is this spatial coverage that you can get. To obviously, with moorings, for example, you can't get that at all, that kind of spatial coverage. With satellite altimetry, for example, you can, but only at the surface. So, and not necessarily with high resolution. So that's really the only point I wanted to make using this particular slide. Slide 9. Now we're going to shift to the lower limb, and we're going to march our way back southward. There's a particular challenge for the lower limb observationally, because there's at the surface we have many surface drifters to use to define the pathways of the AMOC circulation. But at depth, we have an order of magnitude fewer. Here we have to rely on subsurface profiling floats, such as Argo floats, and the acoustically tracked floats that I described at the beginning, the RAFOS floats. And then, of course, we can still do our simulations. But for observations, we're much more limited in coverage. So in this slide here, you see these are the trajectories of about 60 profiling floats that were deployed in the Nordic seas, all the subbasins, and to look at a large scale, on the largest scale, look at the circulation patterns here. And the only point I wanted to make here really was what they did is they also were able to do some mapping and actually estimate transports in these various internal recirculations or gyres that you can see in the individual basins, where the flow is very bathymetrically constrained. But they can use floats actually to, if you have enough, to make transport estimates. And they found that in these gyres, there's something on the order of 15 sparedrops going around, which is pretty high, especially compared to the dense water, which is now what we're looking at, the cold and dense water. Going over the sills is on the order of, all the sills is only on the order of about 5 sparedrops, 5 or 6. So you've got this very vigorous circulation in the Nordic seas, but only a small fraction of it actually a fraction of it leaks over the sills into the North Atlantic. If we could move to the next slide. Okay, just like for the upper limb, the intergyre region is of particular interest. To look at the connectivity of pathways from one gyre or region to another. So now here we are in the lower limb, moving from the subpolar region to the subtropics. And certainly, historically, the primary pathway for the southward transport of North Atlantic deep water component of the AMOC was the deep west was thought to be the deep western boundary current. And but observations starting in the 2000s, I would say, started to question whether that was really as direct as it looked in the Stommel-Ahrens theory. And in this figure, you see the trajectories of about 55. These are acoustically tracked RAFOS floats deployed in the deep western boundary current at 50 north. Heather, if you have a pointer that can point and you can point to where they were deployed, that's great. And they are color coded by temperature, essentially. So they start out cold, and then you can see that the ones that move the furthest south actually get warmer. And these were at the Labrador seawater level.
Amy, 2 minutes.
Thank you. And what they show is that, first of all, a large amount of recirculation in the subpolar gyre, and also, though, these interior pathways. And very few of the floats actually continued continuously along the boundary. And so this opened up new ideas about the interior pathways, which are important because they change the mixing history of waters following interior versus boundary pathways. And they also tell us that by monitoring the boundary currents alone, we might not be capturing all of the lower limb of the AMOC. Let's see, okay, slide 11, lower limb. I'm going to skip that one, Heather. I'm going to go to slide 12. This is the lower limb subtropics. These show some trajectories of floats, a few floats, 3, that were deployed between 1,200 and 3,000 meters, definitely North Atlantic deep water, on the western boundary. And the main point here is to show how non-continuous the deep western boundary current can be. These 3 floats all kicked off the boundary at a particular topographic feature. And in one case of an anticyclonic coherent deep eddy, can't see this from satellite altimetry, was formed. Okay, slide 13. There's almost no Lagrangian observations in the South Atlantic at deep levels. And so we pieced together something for the paper, which I welcome you to go and read about, but I think I will jump to the last slide. Slide 14, which shows the schematic that we pieced together from these various Lagrangian studies. And we had 4 basic points at the end of the paper that we wanted to make. The first, that the Lagrangian viewpoint in particular helps to illustrate. Recirculations and interior pathways. The floats clearly, and floats in the simulated trajectories clearly trace out recirculations and interior pathways of AMOC components, and those recirculations slow down the meridional progression of these water masses because they're circulating for a while before they continue on their meridional journey. Another major thing that these floats in particular show is the importance in some regions of coherent eddies, both near the surface, where we also can see these eddies with altimetry, such as Agulhas rings, North Brazil current rings, but also at depth where we cannot see them with satellites. There are several examples in the paper of where eddies are shown to be an important part of the AMOC. And then I just finally, again, want to mention about the value of numerical simulated trajectories, because they can be done forward and backward. We can put in thousands of them, but in the end, they need to be verified with observations. So I think I'll end there and take questions.
Thank you, Amy. A reminder, if you have a question, use your raise your hand button, or you can type it in the chat box. So we'll take the next 10 minutes for any questions. All right, I see a question from Mike Patterson. Go ahead.
Hi, Amy.
Hi there.
Nice presentation. On the South Atlantic, I'm curious about, are there plans then for deployments of the RAFOS floats in that region? And to what degree do the deployments of the Argo in the South Atlantic, could they be, or are they being used for looking at these, the deeper level recirculation?
Right. certainly the Argo floats to the extent that they reach deep enough, but that most of them drift, I think, at deepest 2,000 meters. So you're just in the upper part of the North Atlantic deep water. And you're not at anywhere near the Antarctic bottom water or the North Atlantic deep water. And we have made plans occasionally or sketched out ideas for RAFOS deployments at deeper depths. RAFOS right now are the only floats that can go sort of below 2,000 meters. Deep Argo is coming online, but it's going to be a long time before we have many enough floats, to put together a statistical description of what the pathways are. So right now, the RAFOS floats are the only one, and we don't have any funded plans to do that. We have lots of ideas, but we don't have any funded plans yet.
And what I'd say is that as we're looking at our meeting next year, and we're looking to the future and setting the stage for what future investments for the observing system downstream, this might be something that is particularly highlighted.
Yes, there's two particularly interesting things along the western boundary that are really undescribed or ill-described, and that's the breakup of the deep western boundary current off the coast of South America, and then its apparent coalescence again into a boundary current near the Victoria Trinidad Ridge, and then separation from the boundary and eastward drift towards Africa. And all of that could really benefit from a Lagrangian approach.
Great, thanks.
I see a couple of comments in the chat box or questions. One from, is it Aishu Hu? Says, very nice talk. By the end, do you think the MOC does or doesn't look like conveyor belt?
Does not. Not at all. It has, I think of a conveyor belt as like this rubber belt, right, that goes around in a circle where something that happens in one place, is instantly communicated to the rest of the belt, and it really doesn't look that way. It also isn't just this two-dimensional circulation system. It's very three-dimensional. And also, what the conveyor belt doesn't emphasize at all is the importance of eddies and mesoscale variability.
A comment, I think, from Ranellas Perez. Greg Johnson at PMEL has deployed many deep Argo floats in the Brazil basin. Would be nice to deploy deep Argo floats and RAFOS floats further south in the subtropical gyre.
Yes, yeah, it sounds like a good idea. I wasn't aware that there were many deep Argo floats in the Brazil basin. That's great to hear, though.
A question from Devanarayana. Thanks for the great presentation. It's nice to know about RAFOS. Any plans to deploy them in Pacific? It might be interesting how these waters move in Pacific.
Absolutely, it would be great. There have been, over the decades, at least one, maybe two regional RAFOS projects in the Pacific, but it's a huge basin. And yes, we just would love to talk to interested folks about that. We here at WHOI are in a position to support new observational studies anywhere in the world. We build the sound sources for tracking. We can provide tracking services. We can provide advice on the floats themselves and how they can be acquired. So we're happy to advise and assist any PIs who might be interested.
Okay, and a question from Zoltan. What is known about Lagrangian observations for the subtropical North Atlantic and its layers? You passed over this region in your talk.
I did, yes. Sorry about that. Well, as far as the AMOC goes, the Gulf Stream is the primary northward pathway for the upper limb, and the Lagrangian observations show that as well. For the deeper limb, we have some float trajectories, part of one regional study that show, again, at the crossover between the Gulf Stream and the deep western boundary current, there's a lot of exchange with the interior. So the straight southward path along the boundaries is definitely interrupted there at the crossover.
And I think Paola Chessie had a question. You want to
Yes.
go and ask?
Hi, Amy. Thank you. Very nice talk. I have a comment more than a question, and that is that we've just recently completed a Lagrangian analysis using the echo assimilation, of course, looped for a longer time than the 25 years that echo has. And echo has all of the AGO flows in addition to in situ observations. And we've taken that to the for the upper limb. Just at the moment, we've only completed the part that relates to the upper and lower, to the upper limb of the AMOC, so addressing the warm versus cold route. And with these data, of course, interpolated, which is coarse resolution, but it's very well constrained, I think, by data, we get a very different transport, a very different partition between the warm route and the cold route, with most of it coming through the warm route, the vast majority. And we trace that back all the way to the Pacific. So this is published in GRL. I don't want to take your time, but it just came out. So,
good. Oh, I'll look for that. That sounds interesting. Yeah, thanks, Paola.
You're welcome.
Okay, we have more questions in the chat. Peter Rhines, do you want to ask your question out loud? I'm not sure if I get it.
Okay, I'm out loud now. Do you hear me?
Yes.
Oh, that's great work, Amy. I'm 3 years since I graduated from oceanography, but I'm really watching this. A half century ago, we had a meeting at Woods Hole trying to bring together Tom Rossby's floats at the time with tracer people. And what is now being done to bridge between Lagrangian trajectories and tracers, particularly the dynamic tracers, theta S and potential vorticity? And I have an axe to grind, of course, stressing what I think is a value of transport sections on the theta S plane, which lead us to water mass transformation as well as circulation. Thank you.
That's a big topic, and I don't have a short answer to the to your question specifically about what's being done, about sort of comparing or bringing them together. There was some work done by Susan Locher's student at the time, Stefan Gehry, about comparing, trace what you learn from tracers versus Lagrangian observations. But we probably should chat more offline about that one.
Okay, it's tracers are like what's the word? Billions of your very
floats. Yes, understood. Right. But you don't have their trajectories.
No, that's right.
Yeah. So yeah, the great thing about the trajectories too sometimes is they reveal processes as well as pathways. So they can show eddy formation or other processes like that.
There is the train of research, like Jake Gebbe and others, who are tracing tracers back to their origins at the sea surface. So that's certainly not the lovely detail which your work reveals, but certainly also some endpoint connections.
Yes. Agreed.
All right. So I see two more questions. So let's conclude with those two questions. But first, a comment from Renelas. Thank you for the presentation. As a follow-up from Greg's paper, 31 deep Argo floats were deployed in the Brazil basin.
Oh, okay. Oh, wow. That's a lot. Okay. Thanks.
Okay, so another question from Chris Wilson. Have you identified any systematic differences between observed trajectories associated with the AMOC and offline trajectories driven by eddying ocean models?
Any systematic changes? Sometimes I think I have to answer that question as no, because sometimes the number of observations is so relatively low that statistically speaking, we cannot distinguish, say, their probability distributions from that of thousands of numerical particle trajectories. they fit, like they're consistent with, you know. So we have not, as far as I know, I'm racking my brain, we have not found somewhere yet where we can, with statistical confidence, say that there's a difference. I hope that answers your question, Chris.
Question from Jose Valencia. Nice talk. What are the pathways of deep water filled Caribbean basin?
What are the pathways for deep water? Well, the deep Caribbean is, well, I'm not super familiar with all the passages. The deep Caribbean is somewhat closed off from the North Atlantic. The deep western boundary current certainly travels to the east of the Caribbean along the boundary. Those three floats that I showed with them spinning off the boundary into the interior and making an eddy are examples of that, going east of the Caribbean.
Okay. And I really hate to cut off any questions, but do we have time to take one more, Amy?
Fine with me.
Okay. A question from Devanarayana. In the figure that represents the Lagrangian currents, it seems there are strong warm currents near Greenland. Any thought on shelf ice melting?
That's a good question. That's certainly an area of active research. And you know, the extent to which those warm subtropical waters, which do get cooled as they flow around the subpolar gyre, but are still, you know, bringing heat to near Greenland, that's an area of active research. But definitely that has been postulated, that those warm currents can have a significant impact on Greenland melting, especially of the glaciers that I forget what they're called, but where the glaciers come out and go out over the ocean, so their underside is exposed to the ocean. You know, if you bring warm water in under those, you know, that could accelerate and accelerate the glacial speed as well.
Great, thank you, Amy. I think that will wrap up our Q&A for today. So thank you again for the presentation, and thank you everyone for participating. I think at one point we had close to around 90 participants on at this webinar. So let's carry that over to the next AMOC webinar, which will be on October 15th. That talk will be by Gerard McCarthy on the paper Sustainable Observations of the AMOC Methodology and Technology. So we hope to see everyone there.
Thank you, everyone.